for having me. This is my first international trip since COVID hit. So I had to get a new passport. I had to remember like how to sleep on a plane. So it's really good to be here. And I'm in town for a conference where we're all sharing results from the Webb Telescope. And that part's been really fun too, to find out what folks are learning with this new telescope, and just kind of, it's like being a kid at Christmas, but it's better. So I want to talk to you today about the telescope. I'm going to keep the lights kind of up, and if we're having trouble seeing, like with the contrast, we can lower them. But the only settings they have are snooze and really bright. Okay, so let me know if we need to turn it down for a bit. Oh, and by the way, everything I'm going to show you, all the pictures are real, and except if it's a simulation, I'm going to be like, this one's fake, okay? But otherwise, everything's real. Both of those pictures are real. That's a picture that the telescope took of itself. It can take its own selfies. So in gray, I have the telescope selfie. That's the telescope looking at its own primary mirror. And then behind that, I have data from a galaxy cluster, a group of thousands of galaxies all in a small space out, that was taken back in October, November. Right? So I scrubbed, once we launched and we got the telescope working, I took all of the like artists' conceptions and all the fake stuff, and I tossed it out. So everything in here is real, okay? Unless I tell you it's not. Oh, okay, so who the heck am I? I'm one of the people, there are many people, there were 600 people that commissioned the telescope and about 20,000 people that built it. But I'm one of the people that didn't get a ton of sleep for 6 months while we commissioned the telescope. And I am also a scientist doing, analyzing data from this telescope, okay? So I want to start by just acknowledging what an international project this is. This is a telescope led by NASA, which is a partnership with the European Space Agency, ESA, and the Canadian Space Agency, CSA. And so these are little dots for everywhere any part of the thing was built or was worked on. And you can see that it really is a global project across Europe, Canada, and the United States. And in fact, since I have crossed the pond to get here, I'm going to note both that we have 4 science instruments. One of them was built by the European Space Agency. That's NearSpec, being proudly looked at in 2011. That's actually when it finished. And then we had to integrate it with the other science instruments, and then integrate it with the telescope, and then integrate that with the spacecraft, and build it up these bigger and bigger pieces. But that was, NearSpec was built by ESA, and it's working great. And then Miri, the mid-infrared instrument, was built in the UK. It's a partnership between the UK with some contributions from the United States at the University of Arizona and JPL. But there it is being unwrapped when it shipped over, and it shipped on British Airways. They told the pilot how much the thing was worth, and the pilot said, "Okay, fine." Put it in the hold very carefully, and brought it over to where I work at the Goddard Space Flight Center. So that's Miri. And then the other 2 instruments, one was made at the University of Arizona, and the other was made in Canada. So really the science instrument package on this has been a very multinational undertaking. And I just want to acknowledge the Miri team, since that was the instrument made in the UK, led by Jillian Wright. And that's much of the Miri team in Baltimore during commissioning of the observatory. Okay, so first I'm going to tell you why we built the thing, like what is the point, and then I'm going to show you that we're doing what we said we would do. So the Webb Telescope was built to do 4 big things. The first of those was the elevator speech, right? Whenever you have a big idea, you're supposed to have a really short pitch that you can do in an elevator. You never tried that? Elevators aren't that long, right? So, okay, what do you want to build? We want to build a telescope to see what galaxies, see, I already messed it up. We're already at the top floor. All right, so let's do it again. What do you want to do? We want to build a telescope to look back in time and see how galaxies formed. Okay, that's the elevator pitch for JWST. And we're due it for the Webb Telescope, or JWST, which is what astronomers usually tend to call it. So it's peering back in time. And I will show you that and maybe talk a little bit about how we can do that, because it seems like magic, but it really does work. So let's look at each of these in turn. Actually, let's just dive in. This is the overview. Let's dive in. So this is we're actually doing it. We can look back in time to see what the misspent youths of galaxies were like. And we can do that just because telescopes are time machines, right? We can't, if you think about on a sunny day, and I saw the sun for all of 3 minutes today, so that was good. The sun's about 8 light minutes away, right? So light takes about 8 minutes to get from the sun to us. So that means the light you're seeing is 8 minutes old, right? Okay, who cares? Sun's the same 8 minutes ago. Now think about Jupiter. Jupiter's on average about 40 light minutes away. Again, not that interesting. Jupiter's pretty much the same. But now if we start thinking about nearby stars that can be several light years away. So the light we're getting from those stars left that star several years ago. Okay, Vega, how many people can find Vega in the sky? Really bright star. Okay, well, we'll teach you that tonight. The constellation and the open viewing. Vega is about 25 light years away, all right? So the light that you're seeing traveled through space for about 25 years. Great, none of this is interesting yet because the universe hasn't changed in 25 years. But it has changed if we can look back to see galaxies that are billions with a B of light years away, right? Once we get to billions of light years away, we're starting to see back in time over a good fraction of the history of the universe. The universe is about 13.8 billion years old. That's a good question to ask me in questions. How do we know that? And so if we can look back and see galaxies like this, we're seeing billions of years in the past. So the white galaxies in this image here, we're seeing as they looked about the time the sun was formed. And then behind that, the galaxies we see in red, we're seeing as they looked 11, 12, 12.5 billion years ago. And the galaxies that are linked with there's little squares around them, the furthest one of those in this image, we're seeing as it looked 13 billion years in the past. And so this is what we do when we're studying how the universe came to be, is we go look back in time, and we can't see our own past. It's not that kind of time machine, right? It's not a Marty McFly time machine, but it's a time machine that lets us see other galaxies past. And then we make an assumption that that over there is a lot like over here, that there's something special about our part of the universe. And that lets us look back in time and see how galaxies like the Milky Way came to be. And then even better, we can take spectra, we can look at the rainbows of each of those galaxies to understand what those galaxies were like inside. And so the little blips over there are divots in the rainbow that tell us about in this case, the oxygen and the hydrogen within those galaxies. So that was the elevator pitch, and that was the image, that was our first science release image that we released last July. And in fact, the White House liked it so much that the President of the United States released the image. So that was pretty cool. And then so that meant in our first science image, we were already showing that we did what we said we would do. The telescope can see back in time to study how galaxies came to be. We also can study how galaxies evolve through the subsequent 13 billion years of cosmic time. Now, we never get to see an individual galaxy evolve because we don't live long enough, right? You can watch our galaxy evolve, but it takes 200 million years just to go around one time. That's a long time to wait. But what we can do is we can look back in time at different snapshots of what galaxies were like 1 billion years ago, 5 billion, 10 billion, right? And really start to get to you have to piece together those snapshots to understand how galaxies have evolved with time, right? So that was goal number 2, doing it, obviously. We're studying galaxies. And we're also seeing, what you're seeing here in this sort of ghostly blue stuff is the dust and the gas in this galaxy, that where each of those little holes is probably where a supernova, an exploding star, blew out the gas around it. So we're studying how galaxies evolve. And then that bright thing in the center is an accreting black hole, right? So it's a place where a supermassive black hole is accreting new gas. And then in that spinning accretion disk is glowing white hot. Okay? So our third science goal was to study how stars came to be. And we did that again in our first week because we were on a roll. So this is the cosmic cliffs. You can now find this everywhere. I got the scarf. It's really, stunningly beautiful. And in fact, all right, I'm gonna kill lights for just a sec so we can take a moment to appreciate. There we go. Right. All right, that's a little better. Right. So this is real. We're not making this up, right? And yes, you can go download the raw data if you feel like it, and convince yourself that, yeah, this is just what the sky looks like in that direction. What we've got here going on is a place where baby stars are being born. And you can, in fact, see like the seashore, right? In the blue, you have a place where the hot, massive stars have blown all the gas out. There are these hot stars that are like 10,000 times as bright as the sun. And they blow out all the gas around them, including the gas where they were born. So they're kind of ungrateful little babies, right? Because this is the cocoon where new stars are being born. If you look at the tops of the cliffs, you can see like that bright star right in the middle is a very young star that's just been born. And in this cocoon of gas, and then it's blowing out, and it's actually probably, there are more stars being born in that right on the shoreline than you would expect, because the massive stars up at the top are compressing all the gas. They're blowing all the gas away from them. And that means that you get the gas compressed, it forms new stars. And so there's this complex interplay of stellar birth and stellar death, and then in that stellar death creating new life. That's all going on in this image. Again, we were just getting started. Okay, we also, I'm going to go back to colloquium mode if it's going to let me. Okay, this one's not quite as beautiful. Can you see that okay? All right. So we also can study planets orbiting other stars, which sounds like ludicrous, but it's a thing that we do all the time. We now know that planets are about as common as stars. So when you look up in the night sky from a really dark spot, you can see a couple thousand stars. Statistically, there are that many planets orbiting those stars. That's about how common planets are. And what we can do is, on the left, you can see that we can just monitor how bright is the star, how bright is the star. And then it gets a little bit fainter, like 1% or 0.1%. And it gets a little bit fainter when a planet passes in front. So this is a really cool trick, right? We can then take the rainbow and see how the rainbow changes as the planet goes in front of the star. And then we take the difference, actually, between the rainbow when the planet's in front of the star and the rainbow when the planet's off to the side. And that difference is the light going through the atmosphere of the planet, which means we can study the atmospheres of planets orbiting other stars. And it's ridiculous that this technique works, but it does. So that was what we built the telescope to do, and it's working. So I'm going to spend a couple minutes showing you what it looks like and how we got it there. I'm actually going to skip this other than to say, yes, what is the telescope? It's a lot of stuff. And I'll tell you a little bit about the engineering feat that was needed to get this to work. This is arguably a more difficult engineering challenge than anything else, because we have a telescope that has to be extremely cold, 40 degrees above absolute zero. I don't speak Fahrenheit that cold, but it's like minus 400 something, right? Really, really cold. And then the warm part is like room temperature, or even close to boiling hot. And so we have this sun shield in the middle that has to separate the hot and the cold parts of the telescope. And that has to work like 1,000,000:1 sunscreen, right? Actually, I'm going to use the laser a little bit. This thing, the sun shield, is the size of a tennis court. It deployed in space, and it keeps the hot, hot, hot part down here separate from this very, very cold part down here. So the whole telescope had to be stowed for launch because it's bigger than its rocket. So it really is a transformer, and it now is out at about 1.5 million kilometers away from the Earth, never to return. It's in that orbit for the rest of its life. And it works in the infrared, so it sees light that is about the red of these chairs, right? That's about the bluest light it can see. And then it sees light out into the thermal infrared, out to 30 microns, right? So it sees redder than we can see, but there's something special about the light our eyes can see. And that light is particularly good for understanding the very, very different universe, the very, very distant universe, so very far back in time. Okay? I want to just show you a couple pictures to convince you what an engineering feat and what a human undertaking building this thing is. So this is the telescope nearing completion out in California, and I put in pictures with people just to give you a sense of scale. The thing is 6.6 meters across, and that secondary mirror, this thing with that's the secondary mirror up here. So there's a giant primary mirror, 6.6 meters across, There's a little secondary mirror that all the light bounces off of that's on a little three-legged stool, and that had to deploy out in space. And you can see the people for scale, and then these three mirrors, and these three mirrors were folded behind the telescope for launch, and then they deployed. So just a sense of scale. Each mirror is about a me across minus my fingertips for scale. I'm a short human, but still, right? Pretty big. And there's 18 of them. I love this one because it gives you a sense of scale. Again, this is in California when we were packing it up, but just a sense of how mammoth this telescope. This is a pretty big telescope for, like, if it were on the ground, but it went to space. So it's 7 times the collecting area of the Hubble Space Telescope, and it weighs half as much as the Hubble Space Telescope. And it had to be that light so we could get it into deep space. Here we are testing the secondary mirror. The secondary mirror is up here, and you can see these 3 arms. That's the hinge that unfolds to let the telescope out. And so I will tell you, my nightmare about the whole telescope was that that would never come out. And we'd have this beautiful telescope in space, and the light from distant galaxies would just bounce right off that beautiful gold mirror and right back out to space, you know, never to be collected. That didn't happen. A lot of engineering work went into making sure that one little hinge would deploy when it needed to. It was nice and warm and toasty the whole time, so it couldn't ice up. A tremendous amount of work to make sure these deployments worked. And this is the most complicated set of things unfolding or things, you know, of deploying in space that has ever been done. There were more than 100 pieces that all had to work together, or we were going to lose the mission. These are the science instruments. These are all 4 science instruments before we bolted them onto the back of the telescope. Here we are getting ready to bolt them onto the telescope. Here are the 4 science, just for a sense of scale, right? These science instruments are collectively bigger than a person, and then they just get bolted onto the back of the telescope where you can see the gold here. This is the telescope pointing down in the clean room in Maryland. Here it is with this sun shield. The sun shield is the size of a tennis court. It's made of the material, it's aluminized plastic. It feels a lot like a crisps packet, honestly, okay? Like that aluminized plastic, but it's not. It's very thin, and it all had to fold up for launch. And then these arms deployed, these arms pulled out after these big pallets unfolded. So they were up like this and then folded down, right? So here it is, about ready to get shipped after we tested that all 5 layers of the sun shield deployed correctly on the ground. But of course, we can't test them in a vacuum, and we can't test them in 0 gravity. So we have to figure out how to do the test in a way that will simulate what it will be like when it's in space. We did test the mirrors and the science instruments in the world's largest thermos bottle, which required a couple trucks of liquid nitrogen every day during a hurricane. It rained more than a meter in a day while we were testing it, but kept the hardware safe and tested that the telescope would deploy correctly in space, as indeed it did. All right, here it is all bundled up for launch, getting ready to be shipped down to French Guiana. And then it went on a custom ship. We trusted this driver, so he got to drive it where we loaded it in California and where we unloaded it in French Guiana, because he was a good driver. And it went in this custom ship all by itself through the Panama Canal. And then, sorry, this is them unloading it in French Guiana, launched from the Ariane Space, a French spaceport in French Guiana. All right, so if this will play, I think I have to push a button. So right now, the telescope is, 1.5 million miles away, and doing science. It's been doing science since July 1st, and it's in this funky orbit where it follows the Earth, but it's never in the Earth's shadow because we're solar powered, right? And this is the thing that we did in the dark over a course of 2 weeks from Christmas 2021 for 2 weeks of deploying this telescope in space. Now this is all going to happen, it's an animation. In fact, every step of this we would stop, hold a meeting, decide we were ready, and go ahead with the next step. So every step was commanded by hand, but the telescope had to do it by itself. There's no astronauts out here, no person's ever been this far out. So I'm going to play the animation. That's the solar panel, which we saw. Okay, this part's fake. This is an animation. This is the solar panel coming out. Here are the pallets that held the telescope, that held the sun shield. We lift the telescope away from the sun shield because we want the telescope to be cold and the sun shield is kind of hot. And then we cinched up these cables to cinch up the sun shield, and easy peasy. Secondary mirror comes out, and the wings of the primary mirror comes out. Okay, fine. What could be harder? This is easy. There were more than 100 pieces that were single point failures. If they failed, we were not going to have a mission anymore. And this thing was tested very extensively on the ground to make sure it would work in space. And it's working flawlessly. It's an amazing testament to the engineers that designed, built, and tested this thing. Okay, and just to show this, because this shows the telescope correctly in the dark. So a thing you can know, anytime you see a picture of our telescope and it shows the big mirror all shiny, I'm not going to do the animation again. Tell people that they're wrong. The telescope's in the dark, right? Those mirrors will never see the sun again, at least until the end of the mission. So what is the telescope doing in the dark? So this is just I want to take a moment to talk about why this is a big deal. This is at least the most important telescope since Hubble, I believe. Now, we have to back that up by making a lot of discoveries, and that's what we're in the process of doing. We're carrying out the first year science operations, the first of, I hope, many. But this telescope ought to be a big deal. One, because it deployed in space, and that's the sun shield, that's the solar array deploying behind me. If that hadn't come out, we wouldn't have had a mission within a couple hours. The fact that it deployed in space means that we can build telescopes that are bigger than rockets, right? We've never been able to do that before. Hubble is exactly the size of what will fit into the shuttle, the space shuttle's payload bay, right? Now you ask, why is the space shuttle's payload bay that big? It's to fit the spy satellites that look a lot like Hubble. But still, right, that's the biggest we could cram it in, but it's limited by the width of the space shuttle, right? Well, this telescope is bigger than the rocket that it rode to orbit because it deployed in space. And it was designed to be really powerful. It is. It is at least 100 times more powerful than Hubble and Spitzer, its predecessor telescopes. And we've been able to demonstrate that the actual performance of the telescope basically across the board is better than we predicted. Okay. And the other reason it's a big deal is that the science goals that we're tackling are just fundamental. We're asking about how did galaxies like our Milky Way come to be? How did galaxies evolve over time? How do stars form? How do planets form? And what are planets like, both in our solar system and in other solar systems? So that's why it is a big deal. We made the front pages of pretty much every newspaper in the world the day our first images released. NASA collected a lot of them, and I grabbed a few of them, just showing the reach of this telescope. And it's also providing good news at a time when I think the world could use some good news. And now what's happening is that the science papers are just rolling in, and it's been really, really, really fun. I want to make sure I leave time for questions, so I'll just summarize this by saying that we have fuel on board for at least 20 years. We don't know how long the telescope will last. We can talk about that, but we don't have a known end date. What formerly was the limit was how much fuel, propellant we carry on board, and that's more than 20 years. Okay, so I'm going to geek out a little bit about science, and then we can stop and take questions. All right, so it's actually really hard to observe targets that are moving, that are in our solar system. We're concerned about whether we could do Jupiter because it's so bright, and then this popped out, and we're like, all right, fine, we can do Jupiter, great. So that's fantastic. We can do planets in our own solar system. Actually, can I kill the lights for this one because it's really pretty? All right, let's go to, don't fall asleep. Thank you. All right, gorgeous views of Jupiter, just fantastic. And this, see the planet? Right, there's Neptune, our friend Neptune, and then making it bigger just so we can see. And I really like this previous image because it shows, Neptune just, minding its own business in a sea of galaxies. We hadn't seen a view of Neptune that good since we sent Voyager there. right? More than 20 years ago. We have great performance. The images are sharp. They're twice as sharp as we expected them to be. And you can just see the difference here. On the left here was our previous telescope, Spitzer, in the infrared, a NASA mission. And on the right, you can see that same field with JWST, with the Webb Telescope. And just, which one would you rather have? Just gorgeous, both deep and sharp views of the universe. Okay? And I do want to just point out that, every time I see an image like that, I see this. This is the best team photo ever, okay? This is a picture of the team that built the mirrors. And when they were done building the mirrors, they took a selfie. And they got Chris in the middle to take the picture for them. But it's such a neat, there's, a couple decades of work for each member of that team. And there they are building the mirror. And then somebody taking a picture of them. So yes, okay. So zoom. I'm mindful of time, but I can't help but show you this. This is Max 0723. This was the image that Joe Biden released. And you can spend as much time as you want. Download these images, and they're on NASA's website, and just start zooming around. They're so beautiful, right? This is what the universe really looks like. You've got this galaxy like here, the sparkler, and this galaxy right here. Look at this thing, right? This thing is forming star clusters all along it. And we're seeing it as it looked several billion years ago. And then this little guy right here, this little red speck, we're seeing as it looked 13 billion years ago, when the universe was only about 0.7, 0.8 billion years old, right? And that's the spectrum that shows that that's true. These rainbows, this spectroscopy, breaking up the light into its rainbows, is a really important part of our science mission, because we're figuring out what stuff is made of. These are all the elements that this galaxy is made of. We're also finding galaxies that are just done forming stars. They are done. We don't know why they finished forming their stars, but it's really cool. And then these were the record holders for how far back in time we could see. This is 320 million years after the Big Bang, so seeing back 13.4 billion years. And then that record, which is just, gorgeous. And we can see that because this rainbow, the color of the spectrum, tells us, yes, indeed, that's how far away that galaxy is. It actually tells us, it tells us how much the universe has expanded between now and then, but you can ask me that question if you want to know. And then we're just taking fantastic spectra that are showing us what these galaxies are made of, about the oxygen, the helium, the magnesium. This is all the stuff we're made of. And it's being made in stars 13 billion years ago in this galaxy, and then cast out into the voids to be formed into new stars and planets, and that's how you get us. Okay? One more zoom in, because I can't resist. This is my favorite picture that we've taken so far. This is Pandora's cluster, and you can just spend as much time as you want zooming in around these galaxies. They're gorgeous, right? And again, the white stuff is in the foreground. That's the galaxy cluster, and then all the sort of reddish galaxies are behind it. It's just shockingly good. We're also studying what exoplanets are made of. This is the atmosphere of a planet. This is the spectrum of an exoplanet telling us about its atmosphere. And the point here is just that all of these different colors are molecules. And we're studying the chemistry of the atmosphere of another world. And we're doing that for samples of dozens of exoplanets. So that's really neat. We're finding out what other planets are like. Okay? And it just goes on and on. We're taking fantastic data every day. We're executing 500 science programs in the first year of observations. This, I think, is like a terrifying galaxy, but this is a galaxy where you're seeing, do you see that hole right there? Right? That's a place where supernova, at least one or more supernovae, exploded and blew out all the gas, right? So these parts are all the gas and dust, and for this part, it's just blown out. You can actually just start counting bubbles. There you go, there you go, there you go, there you go, there you go. These are all places where stars have blown out the gas, which can then stop future stars from forming. Okay, so I am mindful of time, so how about we do, we'll leave you with this really pretty one, and then we'll turn the lights on so it's not super dark, and you can ask me questions. How's that? No, that's outreach. That's very bright. Try that. Okay, good. All right, thank you. So, would anyone have a question? Early adopter, go for it. Mm-hmm. Why is Triton so bright? That's a good question, and I don't know. I don't know, but I can go ask Heidi, who took the data, and I can get back to you. I'll put it on Twitter. Okay. All the way in the back. Do I believe there are aliens? The closest I've ever come to aliens has been in Hawaii when I went snorkeling, and they have these manta rays. Manta rays are like 14 feet long, right? And they have like a thing that sucks up the plankton that's like this big. And they have these lights on the floor of the sea, and so the plankton come, and then the zooplankton come and eat the plankton, and then the manta rays come, and and you're sitting here staying really still, and these giant manta rays come right up in your face, and they electrically sense you. So if you stay really still, they'll like flutter up against you and like check you out. And so part of me thinks if that can exist, then what else is out there, right? Or at least that's how wild Earth can be. Are there aliens? Nobody knows, but we know that there are 100 billion stars, give or take, in our galaxy. We know that there are hundreds of billions of galaxies in the observable universe, and that we know that in our own galaxy there are about as many planets as there are stars. So either there's, either life is vanishingly rare, and we got really lucky, or life is common, in which case there ought to be many planets with life. But we have no idea. We haven't gone out and looked. You're asking about aliens, so you're asking about smart, right? You could argue whether we're smart, but you're asking about intelligent life, right? And we don't know that either, right? But it is an answerable question that we could at least try to find out. And if the answer is that we look at a bunch of planets, and none of them have anything, that would tell us something about how rare the processes of life are. Question from a young man on the way back. Yeah. Can you speak up? Yes, so there are a couple places in our solar system that might possibly, maybe have some sort of life. So Titan is a moon of Saturn. There's also other moons of Jupiter and Saturn, Europa and Enceladus. That Titan is weird. Titan's got liquid oceans, but they're not like our oceans. They're not made of water. So maybe, but it'd be really cold. So that's not where I would bet. I would bet, again, I'm just, anybody can place a bet, right? The oceans of Europa, right? Europa is a moon that has a solid crust of ice, and then underneath is probably a liquid water ocean that's protected from the nastiness of space. And so Enceladus does as well. So there's two moons in the outer solar system that we know have a liquid ocean. And so when we think about aliens, that's where my brain always goes, right? And that's just because, so we have no idea, but it's possible we could send a probe and go find out. The other thing we can do is there are plumes that come out of Enceladus and Pluto. There are cracks in the ice, and then water shoots out. And so we can take spectra. We can look at the rainbows of those of that water that's jetting out, and like seeing what was inside those oceans. And that tells us more about what the conditions are like down there. Oh my gosh, a lot. We're going to go for the overflow seating, which is totally compatible with the fire marshal. Let's tell no one. Good. Yes. Exactly, right? So the question is, if all we get are snapshots, because we never see the universe evolve, because we don't live long enough, how do we piece together the snapshots right? So it's a little like you have one family's baby pictures, and then you have like another family's awkward pictures of middle school, and then you have some other family's pictures of, of middle age and old age, right? And you're trying to see, well, how do humans grow? and you're trying to piece. That's easier. Actually, this is a harder problem because galaxies are more different than humans. We all pretty much look the same, and we kind of, there's far more variation in galaxies. But it's that same problem of how do we figure out the ancestors, who is whose ancestors and who is whose descendants. And in fact, that was a topic we were arguing about at the conference today. One way that you do it is you look at how rare things are, because that relative rareness should continue with time. The rarest spots in the universe will be the most dense parts of the universe, right? And those spots are rare at early times, and they're rare throughout the history. So you can try to match basically how special a place is, how rare it is. The other thing you can do is try to spot the processes that are at work. So you can say, if galaxies, I see some galaxies that are forming stars like very fast, and I see other galaxies that have a lot of stars that are young, but they have a lot of stars that are like toddlers, but none that are babies. And you're like, well, what just happened, right? Something happened to shut off all the star formation. And then you can find the processes that are involved. And we argue about the processes, but some of them might be that supernova feedback that we were talking about, when the supernovas blow up, that they can blow out all the gas. Black holes in the centers of galaxies might also be able to blow out some of the gas and stop the star formation. So we study those processes, and then we try to understand, well, what would that galaxy turn into if it all stopped forming stars? But some of it is a bit of squinting with the snapshots, trying to figure out who turns into what. And it is hard because we never get to see, we just don't live long enough to see it. We have to piece it together from our snapshots. Yep. All right, I'm gonna go this side of the room. Okay, how about both of you in sequence, but you first.
Why are the mirrors chosen to be gold colored?
Why are the mirrors gold? Yeah, it seems extravagant, right? It's not that much gold. Like, it's a couple wedding rings over the whole mirror, right? Why are they gold? Gold is a fantastic metal. It is very, very reflective. It never tarnishes. If you think about like silver, silver tarnishes. I had a, old silverware, right? You have to polish it. Gold doesn't, you don't have to do that for gold. It's just shiny. It's because it doesn't oxidize, right? So that's really well behaved for a mirror. We want a very shiny, reflective mirror. It's also in the infrared where the telescope is working. It's great. It's just very, has a very high reflectivity. So that's why. It's actually, the mirrors they're not solid gold. That would be really expensive. They're beryllium. So they're a metal called beryllium that's been lightweighted. It's actually honeycombed on the back to make it light enough that they're about 40 kilograms. They're not, each mirror is about 40 kilograms. We take 90% of the weight out of it. We make a solid sheet of beryllium, and then we bore out the back in a honeycomb pattern to make it light enough. You can lift it. You might hurt, but you can lift 40 kilograms, right? And then we put that little thin layer of gold on it to make it really, really reflective and very stable with time. So it didn't tarnish when it was in our clean room.
How did you know on the graph you showed just now, it shows the presence of different elements?
Oh, how do you know the presence of different elements? Great question. That's like a planted question. Okay, so the answer is, okay, go ahead. This is the problem of having the animations. Come on. I want to go to that one. Thank you. So the way that you do that is you go to a laboratory, and you take elements that you care about, and then you take molecules that you care about, and you put them in a vacuum, and you heat them up, and then you look at them with your little prism to make a rainbow. And then you take a picture of that rainbow. And you do that for a bunch of different elements and a bunch of different molecules, and then you compare to what you see in the sky. And what an astronomer who's got a plaque outside, Cecilia Payne-Gaposchkin, figured out at Harvard, after Cambridge wouldn't give her a degree, she figured out that the elements that we were seeing from the spectra, the rainbows of stars, were just like those in the lab. And she's the one that figured out that the stars are mostly made of hydrogen and helium by doing the math of what the level. She did the math to figure out how they should glow, right? But really, it's done by taking samples of stuff we want to measure, putting it in the lab, measuring it, and then comparing it. And it's a beautiful thing about the way things work that hydrogen looks the same everywhere. It's got a really characteristic pattern. So any distance, anywhere you see hydrogen in the universe, you're like, you are hydrogen and you can't hide. And the same thing for oxygen, nitrogen. You just do it in the lab and then compare it. All right, let's see. Yes? Do up, and then we'll do you next, okay?
You mentioned earlier, and some of the photos technology. How has that, like, older technology been integrated and had limitations on the newer 2020, 2021 technologies?
So that's a great question. So the question is, parts of this telescope were built in 2011, right? More than a decade ago. And how does that work? So a telescope was designed in 2009, 2010. It passed its critical design review then. So that means it was mostly designed at that point, right? And so, yeah, you have to build these things with the best technology that you have now. And then by the time you finish, key parts of it are already kind of obsolete on the ground, but they're still the best that's in space, right? So our computer on board is a lot slower than the computer that is on, but it's a space-hardened computer that doesn't mind getting zapped with a lot of radiation. The main things that changed are our digital cameras. So the digital cameras that take the pictures, that actually record the light, were state-of-the-art in 2010, but we know how to build much bigger ones now. So NASA's building a new telescope called Roman, which is finishing up now. And Roman has a much larger set of detectors. They're easier detectors too because they work in the optical like your eyes see. But they're still, it's just there are more of them, and they can cover more of the sky because it's because it's semiconductors, right? We've just had more time to get better at building semiconductors. So that's the biggest thing where we notice. We're like, oh, if we were building it today, we would build it with more pixels, more megapixels on board. But that's the best we had in 2010, and it's still by far the best. It's a factor of 100 better than anything else that we have, so it's good. But if we were building another one, we would build it with the best detectors we have now, which then, of course, would go obsolete by the time it launched again. Down front.
Why is the star colorful, like different colors?
Why do stars come in different colors?
Because everyone thinks they're kind of sometimes gold or silver.
Yeah. So why do stars come in different colors? So can we talk about your eyeball, and then can we talk about the telescope? All right, let's do eyeballs first, okay? So the color of a star tells you its temperature. And stars come in lots of different temperatures. And the cool ones are like red, right? Because they're not that hot. And then the hotter ones are yellow to white. And then they get like so blue. And the very hottest stars would burn you, like you would get a bad sunburn, because much of their light is coming out in the ultraviolet, in the light that can burn our skin. And so the colors of stars, even when you see them in the sky, is telling you something about what that star is like. Is it a big star that's going to be big and blue? Or is it a star that's like the sun? That would be a yellow or a white star, okay? And then the stars that are really cold, like a red dwarf, they're actually really hard to see because they're not bright at all. Right? You would think blue is icy cold, but actually blue is burn you hot. Yes, that's totally true. We never know that because there's nothing on Earth that hot, so we're not used to that. But in space, there are things that are, the hottest stars are like 10,000 degrees, right? So hot they're burning blue, right? Yeah. Yeah.
Why can't telescopes take videos? Why is it only for
Why do not telescopes take videos? That's a good question. So they can, but it's not good for what we want to do. For the science that we want to do, we are trying to look at faint things. And if you take a video, it'll be black because you won't have enough light. So an image like this, I'm going to go back to, let's see, let's go for these. These weren't even very long. These are like 500 seconds long, okay? But I needed to integrate, because I took these, so I remember how long we integrated. But for these, so it's about 10 minutes, okay? So we open the shutter, and we hold the telescope really still, and we take a color, and then we're done, and that was 10 minutes. And then we do it again for the other colors, and so we do it one at a time. So this is a, yeah, so we don't, galaxies and stars are too faint to take videos, is the short answer. There's no reason you can't, and if you wanted to look at bright things, then you totally could. And in fact, when we do the Jupiter images, those are a second long. So it's almost like a jerky video. We take a bunch of 1 second, and that's the shortest exposure we can't, that's the shortest exposure we can on board. So in that, we are doing video for like bright planets and asteroids, but it's like jerky, once a second video, right? Okay. Let's see. We have not had anybody all the way in the back, so we're going to go all the way in the back.
Are you still happy to?
I'm fine.
Ask you questions forever.
I'm fine, but we want to let people go so they can go see the heavens when they want to. So you tell me, you're in charge.
Okay, so I'll break the bad news. I'm afraid the clouds have thwarted any stargazing plans. We can see Venus, but nothing but Venus, and we can't just stare at Venus for an hour.
This is like being a real astronomer, by the way. Yes.
This is also why we go to space and we don't do professional astronomy from England.
Anymore, yeah.
Yes, anymore, exactly. So if you want to take a couple more questions.
Well, what do you think? Well, you guys vote. Who wants a couple more questions and who wants to run away? Questions and run away. All right, fine. Yeah, I hear it. It's late for me too. All right, the young person in the back.
Are you planning to send more fuel to the telescope?
Are we planning to send more fuel to the telescope? Can I tell you a story about an astronaut named John? Okay, we don't need to, because we wanted to have a 10 years of fuel. And in fact, we had such a beautiful ride on our rocket that we have more than 20 years of fuel. So we don't know that the telescope will last 20 years. So we're really happy with 20 years. That sounds good. Before launch, there's an astronaut named John Grunsfeld, who's the astronaut that fixed Hubble. And he was very insistent that we be able to put more fuel in it if we needed to. So he made sure we had a little place where, we could stick the fuel in if we needed to, okay? But as it turns out, we had a fantastic launch and we have more than 20 years of life. So I don't think we'll need to. I think we will be ready to build another telescope in 20 years. But maybe we could. It's a long way out. It's 1.5 million kilometers away. So it's a long way to go. But, we could, and we did put gas in here. There's a little opening on the side so that we could do that if we wanted, because astronaut John told us to. Yes? That's a great question. It runs on a mixture of hydrazine, and there's an oxidizer, and I forget what the oxidizer is. It's aluminum something with oxygen in it. And yeah, so hydrazine is basic rocket fuel. It'll kill you. It's poison. Don't breathe it. But we don't use a lot of fuel, right? We have, the main reason we use fuel is to fight the pressure of the sun, believe it or not. The light from the sun is constantly pushing on our giant sun shield, and that twists up the observatory. And so we use gyroscopes to counteract that, but every month or so, we have to fire the thrusters to slow down the gyroscopes. And so that uses fuel. Oh my gosh. Okay.
You said about the ages of stars, so 13 million years, or 30 billion, sorry.
Yep.
And you gauge that from the light, obviously, it's come. How do you know where it started from?
Yes.
You don't know necessarily where it started from.
Because I pulled a fast one on you. Okay, great. Thank you. You're giving me the opportunity to unpull the fast one. Okay. So let me tell you what we measure and then what we interpret. And that's a really great question. I'm going to pull up, where is it? It is right, sorry, give me just a sec. I'll pull it up so we can look at it together. It was all the way at the beginning. Ha ha ha. There we go. Good. Okay, so let me show you what we measure and then what we interpret. So what we measure, remember how we talked about hydrogen looks the same anywhere you see it in the whole universe? Okay. This is, pull it up right here, that right there and that right there are 2 lines of hydrogen. And their spacing tells you and their wavelengths, the colors tell you what they are. You find any astronomer anywhere and they'll tell you, aha, that's hydrogen. Okay, it's very nice. So what we measure, and that's oxygen. And again, if you go sit in a dark room and you stare at enough of these spectra in the little vacuum chamber with your little prism, you get really good at this, okay? It's nothing magical. So you say, aha, that's oxygen, and okay, that's hydrogen. Great. So that's what we measure. We say, aha, I see oxygen and hydrogen. Lovely. And then what we measure is the color of color of that light. And that's the measurement. It's actually the actual measurement is the observed color of the light. We also know what color that light is in the lab, right? In a vacuum on Earth, stick a little prism, what color does the hydrogen light from the hydrogen look like on Earth? Take the ratio of that. That ratio turns out to tell us how much the universe has expanded between now and when that light was emitted. It turns out, and this part blows my mind, but it is true, that the universe is expanding, and it's not just that everything in the universe is expanding, like, you know, we all in this room, we all moved away from each other. It's actually that the space is expanding. And because space is expanding, light gets stretched because it's part of space. And so that light that's traveling through space gets stretched. And so what we measure is the color of the light. We compare it to the color of the light in the lab. The ratio is the redshift, how much the light has been shifted. There's a -1 in there, but okay. Bear with me here. And so what we measure is how much the light has been reddened. We then use a cosmological model to interpret that as a look-back time, how far back in time we're seeing. That is an interpretation based on a cosmological model, in this case based on the echoes of the Big Bang as seen by the cosmic microwave background, which is an entirely different talk that you should have someone come give, because it's really cool, right? We can see the echoes of the Big Bang, and they tell us about the history, the expansion history of the universe. But that's what we do, is we measure the color and we compare it to the color in the lab, and then we consult to a model. So what I measure very, very well is that redshift, and then what we're interpreting with that model is the look-back time, how far back in time we're seeing. Okay, that was a long one. Let's see.
How do you feel about making that the last question? Because so what we do,
Yes.
that's not been here before, as a sort of consolation prize for the lack of stargazing, there's going to be refreshments outside, tea and biscuits.
It's like Southwest Airlines.
It
When they
is.
delay your flight, they give you biscuits.
There you go.
Yes,
We
all
don't
right.
have any little pillows. Maybe we should.
Okay, all right, good.
Okay, yes, there's going to be tea and biscuits followed by a second talk. So maybe anyone that's going to leave, how long are you
That's good.
sticking around for?
I'll stick around for a few minutes, yeah.
Okay, so maybe if you've got any questions, you can come and check. But anyone that wants one, there's going to be tea and biscuits outside, and then another talk in about 10 or 15 minutes. Can we thank our speaker again, please?
Thank you.